Hi, I'm Keenan Casey for TouchPlus.com. In this lesson, we're going to be talking about Wi-Fi 802.11. We're learning a little bit about how this important wireless networking protocol works. You know that wireless has exploded of late. One of the main reasons is because wireless devices support mobility. 802.11 is one of the leading protocols to support wireless networking. In fact, I'd say it's the dominant local area network wireless technology. In this lesson, we'll be talking about the format of 802.11 packets, different frame types and how they work, and the important components of the 802.11 protocol, including CSMA collision avoidance. I'd like to start off by just taking a quick comparison of the different versions of 802.11 in terms of their speed, their range, and the physical frequency at which they operate. You can see kind of the granddaddy of all these is the 802.11b, which was released back in 1999, peak speed of 11 megabits per second. We then moved to 802.11g at a speed of 54 megabits per second in 2003. 802.11n is kind of the current reigning king at peak speeds of 600 megabits per second, although typical is quite a bit lower. It supports both the 2.4 and the 5 gigahertz frequency ranges. Coming up on the horizon is the 802.11ac, which has above a 1 gigabit per second speed and also good range and is supposed to be released in 2013. This is the format of a Wi-Fi frame. It has some similarities to Ethernet frames, but also some significant differences. The first 2 bytes are the frame control field, and this is a field that's further subdivided into things like the version, the frame type. It imparts a lot of information. Next is the duration field, which can be used for a couple things, but one is telling the duration that this packet is requesting to send. Next, there are 3 addresses. These addresses are all 6 bytes long, that is, they're 48-bit MAC addresses. Note that we need more than just a sender and receiver because there may be an intermediate wired access point that has to be connected with as well. Next is a sequence control field. The sequence control field is a 2-byte section that identifies the message order and is also used to eliminate duplicate frames. Next, there's another 6-byte address that's used in ad hoc mode. Then we have the payload, which is up to 2,300 bytes of data. And lastly, there's a 4-byte cyclic redundancy check or frame check sequence. The CRC is used to check the integrity of the frame and make sure it hasn't been corrupted. 802.11 defines 3 different frame types: management, control, and data. Note the different types of frames in each category. In the management area, there are 4 different types: a beacon and probe frames, which are used to communicate the existence of and find access points. Next, there is the association frames, which associate or connect a host with an access point. And lastly, there's an authentication frame type. In this middle area, there's 3 types of control packets. These are frame types that don't actually communicate data, but they're used for data transmission, request to send, clear to send, and acknowledgement, all of which we'll talk about later. And lastly, there's the data frames. This is what we're all about, which is the frames that actually transmit data from a sender to a receiver. First, let's talk a little bit about scanning and association. There are 2 ways to find access points in 802.11. The first way is called passive scanning, and you might think about this informally as keeping an ear out. In this case, access points periodically broadcast beacon frames. You can imagine we might get a beacon frame from access point 1 and also a beacon frame from access point 2. In this scenario, the host then, just by listening, hears that there are several access points in the area. It would then choose which one to associate with. To do so, it would send an association request to one of them, perhaps the one that has a stronger signal strength. The access point would respond by sending an association response frame. And at this point, that host 1 is connected with access point 2 and would send further frames through access point 2. So passive scanning is just keeping an ear out and seeing what you overhear. Another way for hosts to find and associate with access points is through active scanning. In this case, we could summarize the process as, if you want something, just ask. This is how active scanning works. First, host 1 will broadcast a probe request. All the access points will hear that and respond with a probe response. At this point, host 1 can evaluate the probe responses that it's received and choose to associate with one. Again, perhaps the probe response with the highest signal strength. Host 1 will send an association request frame to the selected access point, and the access point would respond with an association response frame. You see that host 1 and access point 2 are associated with each other, and host 1 will be sending its traffic through access point 2. So this is active scanning, where the host itself, the mobile host, is requesting some information about the access points that are in the area and then choosing one. This is active as opposed to the passive scanning, where we just listen. In active scanning, the host will actually solicit access points to communicate with. As you may recall, collisions in any context are bad. In the context of computer networks, collisions are when two hosts transmit at the same time over a shared medium. When that happens, the two packets collide with each other, they get garbled, and nobody gets either packet through. Consequently, collisions result in wasted time and wasted bandwidth, so we'd like to avoid them if at all possible. In Ethernet, that is, in a wired environment, we saw that CSMA collision detection algorithm was employed. You recall that basically that means hosts always listen when they're sending, and as soon as they hear a collision, they stop sending and defer access. Collision detection, however, is quite difficult to implement in a wireless environment. In fact, sometimes it's even impossible. For these two reasons, CSMA CD is not utilized. Number one, it's difficult to transmit and receive simultaneously on a wireless radio. Difficult, and that translates into costly. Secondly, in some situations, based on the topology of the network, there may be two nodes that cannot hear one another, but they can cause a collision in between them, and this is called the hidden node problem. Let's consider this hidden node problem in more detail. Imagine we've got two hosts, host 1 and host 2, who do not interfere with each other. They can't collide with each other. Let's further assume that there is an access point in between them that they can both reach. Well, what happens if we do carrier sense with collision detection in this case? Well, due to the signal strength loss over the distance, two hosts might send packets at the same time to an access point. Those two hosts would not collide with each other, but at the access point, a collision would occur because those two hosts are transmitting at the same time in its radius of reception. Therefore, there will be a collision at the access point. So since collision detection is sometimes completely impossible, 802.11 uses a different approach called collision avoidance. Let me show you one way that that's implemented. Collision avoidance is implemented by using request to send, clear to send packets. The idea is to allow the sender to reserve the channel rather than just sending whenever it wants to. This will hopefully avoid collisions of the big data frames and improve the overall throughput of the system. Here's how it works. If host 1 and host 2 both really want to send at the same time, they'll first both send a request to send, an RTS packet. In the RTS packet, they will request an amount of time during which they'd like to send. If both RTS packets arrive at the access point at the same time and therefore collide, then another RTS packet will be sent. Both hosts will defer access and resend another RTS packet after some random wait time. In response to this, that is, correctly received RTS, the access point will send back a clear to send packet. It will broadcast that to its whole area, explaining who gets the channel and how long they're going to have it. So the advantage here is that CTS packet is overheard by everyone, even though, for example, host 2 couldn't hear host 1. The access point chooses to give the channel to host 1. Now when the access point sends the CTS packet, host 2 learns that host 1 will be getting the channel, and host 2 can defer access to prevent further collisions. After the CTS is sent, the data packet can be sent from host 1 to the access point, after which the access point will send an ACK, at which time host 2 will understand that that message exchange is over. Another mechanism used by 802.11 to improve the throughput is a positive acknowledgment. We didn't use this in Ethernet because we could do collision detection, but in Wi-Fi, we want to make sure that the packet was actually delivered successfully. So this is a way of implementing reliability. Let's consider this example. We have a sender who wants to send to a receiver. This may happen after the RTS-CTS. After a period of time called diffs, data will be sent. And that data will take some period of time to transfer. The receiver will then send back an acknowledgment packet, which is very short compared to the data, after this small amount of time called CIFS. DIFs and CIFS are two amounts of time that are used to synchronize senders and receivers. So we see that 802.11 uses a positive acknowledgment in order to improve the reliability of the protocol. Let's consider the big picture of 802.11. Imagine that we have a sender and a receiver, and then all the other stations that can overhear the two. Let's consider the timing of the different events that take place in an 802.11 scenario. First, if a channel is idle for diffs, then a contention period will begin. That is, the different nodes will fight to decide who's going to get the channel. And they'll do so by sending an RTS. In this case, the sender sends the RTS. All the other hosts within range of the sender will hear the RTS and defer access. They will not try to send. After a short period, CIFS, the receiver will send back the CTS. At this point, all of the hosts that can hear the CTS will also defer access. This may be a different group than the host that could hear the RTS. After another CIFS period of time, the data packet will be sent. So this will be from the sender to the receiver. When the data packet is over, after another CIFS period of time, an acknowledgement from the receiver to the sender will be sent. After this data exchange has finished, all the hosts will wait a diffs period of time where no one is talking, and at that point, the channel is again up for grabs, and some other station may send out an RTS to try to reserve the channel. So this is kind of an overview of the timing and the different pieces of the 802.11 protocol. As we conclude, let's think about this question. How does 802.11 overcome the challenges of a wireless environment? You know, there's a lot of challenges that are inherent to a wireless medium. The 802.11 link layer design includes several key features to address the unique challenges presented by a wireless medium. First of all, we've seen the carrier sense multiple access with collision avoidance algorithm, which includes the request to send, clear to send mechanism. This mechanism reserves the channel for large data frames. Also, we've seen how acknowledgments are used in order to make sure that data packets are reliably transmitted. And lastly, we've seen that there are a lot of management frames, the beacons, the probes, the associations that have to be in place to handle the connectivity between a sender and an access point. And these frames facilitate the process of selecting and joining a Wi-Fi network. These are also problems that are not present in Ethernet. In this lesson, we've looked at Wi-Fi 802.11, the dominant wireless LAN technology. We've seen some of its key features and generally how it works. We've been at the link layer. I'm Keenan Casey for TETSPlus.com. Thank you for watching.